Hello, everybody. This video is to explain what's a base change from one basis to a vector space to another basis to a vector space. And also, if you have a linear transformations, what is the matrix form of the linear transformation with respect to different bases, how to calculate it, uh, how to find it, what are the relations. This is all about. This is the related with the week 3 work for a course in University of New South Wales related with the Math2099. Also, to Math2501 is also a close course as well. The subject, this one is coincides with both subjects. Uh, in week 3, there are so many things to cover, and this is what I listed here, and this week's concepts to cover of those concepts, but my focus will be the base change in this video. And my suggestion is that there are so many solutions in my YouTube, in YouTube, in my own YouTube, and also you have lots of YouTube solutions linked via the Moodle of your course, whatever you like to do. You can fill it up the gaps for yourself. What do you need to learn from those exercise or do some exercise related with the how to prove a linear transformation? And also how to find out the matrix form of linear transformation if the think about the codomain basis as a standard basis or domain basis as a standard basis. And also you need to know how to write down the matrix form if the codomain basis is, for example, B and the domain basis, for example, C. You need to know what's the kernel of a linear transformation, and the dimension of the kernel of linear transformation is called nullity. Image of a linear transformation, you need to know the definition and how to calculate it. And the dimension of the image of the T is called rank. And rank and nullity theorem is a very important theorem. If you have a linear transformation from a vector space V to W, and the dimension of V will be the dimension of the kernel T plus the dimension of image T. So the dimension of the Viz vector space will be the nullity plus the rank will give you the dimension of the codomain. Okay, these are the things that you need to work on for this week, week 3. Now I would like to explain the base change from the start. I'm going to tell you a story about the base change. I choose simple example, but my aim is to try to explain what is going on and step by step without having anything skipping. Now consider standard basis. Standard basis of R2, as we know, is E1 and E2. Let's call this set S throughout our thing. We know that Y basis is important because every vector can be written uniquely as a linear combination of elements of the basis. This is the key idea of the basis, because vector spaces are the linear combinations of the many things, and it is messy. How can we work it out with the vector spaces? And what is the building block for a vector space structure? And we realize that this is a concept of a basis. If you have a basis, you can write every vector as a linear combination uniquely. So every vector is a unique representation, has a unique representation for corresponding to certain basis. As we know, we are dealing with the infinite vector spaces in this course, and we have infinitely many vectors. And because of that, we have also infinitely many bases as well. So if you have any vector, v1, v2 as a coordinates in R2, we can write as v like a coordinate, first coordinate is v1 and then e1 plus v2, e2. This is very natural to do, as we know how to do that. But it is the same thing for the other bases. Now, this vector here called the coordinate vector with respect to basis B. I'm going to use WRT with a shortcut of the with respect to. And to denote this concept, we are going to use the vector notation, and we put like in a bracket is the name of the basis. So this basis is S. If it's another basis, we will put another name. So V will be V1, V2 in a usual vectors is the vector coordinate vectors with respect to the standard basis. So far, so good. Now consider another basis, which is not a standard basis. Now B is a set of the two vectors, B1 and B2. Now this is certainly a basis for R2 because you have two vectors and they are clearly linearly independent. Why? Because there is no lambda such that B1 is equal to lambda times B2, which means they are not multiple because you have two vectors. They are not multiple each other, then they are linearly independent. Since you have two vectors, which is the dimension of R2, you have enough number of the vectors, and they are linearly independent. It means that it was going to span all of your space. So it is a basis. It's definitely a basis. Okay, so this is what I'm saying in this corner. B is given by these two vectors is a basis. Crystal clear. That means that every vector can be written uniquely as a linear combinations of elements of B. So now take a vector. Let's take a vector 1, 1. This is a coordinate vector with respect to the standard basis. Now we would like to write it down, this coordinate vector, with respect to the basis B, because B is different. B is not a standard basis. This means that this is just any vector. I'm just making an example to explain things. I'm choosing 1, 1 in order to be able to make life easier and explain explicitly. This means that exist, and this means unique. I just would like to add here, everybody must know by now, but for general audience, let's repeat again. This means that exists, this means unique. I like to use the mathematical notations. So we have that exist unique alpha 1, alpha 2, such that 1, 1 can be written as a linear combination of the basis vector 1, 5, 1, 6, basis of B. So these coefficients will give us the coordinate vector of this vector. It's exactly the same vector. The object does not change, but the representation of the object change because your basis changes. So how to find out alpha 1, alpha 2? So this equation looks like an equation AX is equal to B. If you write it down the coefficient matrix, we have 1, 5, 1, 6, and we have alpha 1, alpha 2. This times this will be the first row, and this times this will give you the second row. So this is a linear system of equation. What I'm saying, I will say this matrix is a B matrix. And if this is the vector with respect to coordinate vector with respect to basis B, and this is the vector with corresponding coordinate vector corresponding to the standard basis. So this is exactly what's happening here. B times VB, this is equal to coordinate vector with respect to S. So that's exactly, I wrote it this one as a notation. That's all I've done here. No work, just writing down this with this. So how can we solve this equation? Usually we make it up, we set augmented matrix, apply the row operations, find out the reduced row echelon form, and find a solution. This is one way to do it. If you do that, just apply the row operations. So this is the matrix, coefficient matrix, and on the right-hand side, we have 1, 1. This is why we have a line here. This is the coefficient matrix, and this is the B vector. So we want to disposition 0. So if we apply R2 minus R1, then this will be 0, and this will be minus 5 plus 6, that will be 1. That will be minus 5, that will be minus plus 1 will be minus 4, so that's minus 4. We get this one, they want this position 0, so if you have R1 is equal to R1 minus R2, you will get this position 0. You just minus times that. So that is 0. That's how you have an identity matrix here. Minus times, this will be plus 4, and plus 1 will be 5, which is that one. So alpha 1 is 5, alpha 2 is minus 4. That's what we found. The coordinate vector with respect to standard basis with 1, 1. The coordinate vector with respect to standard basis B is 5 minus 4. They're exactly the same vectors, but the representation with respect to different bases are different. That's all. So this part here is completely a coordinate change. That's what we call. Now I would like to make another important observation here. Now, B is a basis. Now, right, this B is a basis. It means that this B is a basis. Maybe you would like to see a little bit here as well. So this is exactly the system. B times VB is equal to VS. This is the system that we are dealing with. And B is a basis, so B is a linearly independent, consists of linearly independent vectors on the column of the matrix. If you have a matrix of like that, it means it is invertible. If it's n by n matrix, then it is linearly independent, consists of the linearly independent ones, it is invertible. So there exists a B inverse. So in this case, rather than solving this way, we can solve some other way as well. Because since there exists a B inverse, we can multiply this equation by B inverse, which will give us exactly VB, right? So if you multiply B inverse from this side, you will have B inverse B, which will give you identity. So you will left only with the vector B. And then since you multiply B inverse, so you will have a B inverse here, that's a B inverse. So this equation is equivalent to this equation. You cannot do such things in general form because you have, first, you may not have a square coefficient matrix, right? In this case, we have a square matrix as a coefficient matrix. In general, if you want to solve such an equation, if you have an inverse of this matrix, if it's a square matrix and have an inverse, then you can do so. Otherwise, you cannot do. In general, that is not the typical solution. In general, the typical solution of the linear system of equation, set in the augmented matrix, apply the row operations, find the reduced row echelon form, find a solution. So we know that from the other work that we've done last week's and the previous year as well. Okay, so this equation is exactly this equation. Let's try to find out this vector from this application. Now we need to calculate the B inverse. Calculating B inverse is easy. I have two things here. One of them is for 2 by 2 matrices, there's a closed formula. For 3 by 3 as well, but the 2 by 2 is much more simpler and you can remember it. And you can figure it out. If you don't remember, you can figure it out in a corner. So the inverse of a matrix A, B, C, D inverse will be 1 over the determinant, which is A times D minus BC. This is the determinant of the matrix. And then you will swap this main diagonal entries, and then the opposite main diagonal entries will be just a negative of them. Not just swapping, but as a negative. So we will swap A and D, and we put the minuses between minus B minus C. So that's a general formula. And if you want to check it out, this is exactly the basis. You need to multiply this matrix with the A, B, C, D. And see, this times this times this will give you AD minus BC. If you divide AD minus BC, you will have a 1 here. From this times this, you have a dB minus BD, so that will give you the 0. CA plus AC, that will give you 0. Minus CB, that is minus BC, plus AD, that's AD. So this one and this one, dividing this number with this will give you 1. So it will give you identity. As you know, identity 1, 1 on the diagonals, and 0, 0 here. In general, if you have a larger n by n matrices, the best, the easy way to do it is just to use an augmented matrix, put the A matrix here, and identity matrix with the same size on the right-hand side, apply the row operations, and then find identity matrix on the left-hand side, and whatever the matrix you find on the right-hand side will be the inverse. Let's do this way and check it out with the other way. So you put B here, you will put the identity matrix here and apply the row operations. You want this position 0, then you have R2 minus 4 R1. You want this position 0, that is R1 minus R2. And when you're doing it, you're doing exactly the same things from here. So minus 5, R2 minus 5 will be minus 5 of this one, minus 5 of this will be here, and there no change for this element here. So R1 minus R2, so you have this, multiply minus and add here, so that will be 6. We multiply this by minus, add here, that will be minus 1. So you have 6 minus 5 minus 1, 1. And how about the other way? How about just directly using this one? So the determinant of this matrix will be 6 minus 5. This is why you have this. And then this one will change. So 6 will go here, 1 go here. And then you will have minuses over this side, minus 1, minus 5. This is 1, nothing will change. So this is 6 minus 1 minus 5, 1, which is exactly what you found here in both different ways. So this one is this one is this one. You can see that is an inverse. So what we found in terms of a basis, so if you multiply B inverse with the coordinate vector with respect to the S, you will find the coordinate vector with respect to B. That's what it is. So that's what I'm doing here. I'm multiplying B inverse times the coordinate vector with respect to S. So this matrix will be this matrix multiplied by 1, 1. 6 minus 5 is 5. Minus 5 plus 1 is minus 4. So that's the vector of B. That's 5 minus 4. That's exactly what we found with this way. So it's exactly the same thing. But then, yeah. Okay, so what we were doing actually is to find a formula, right? All these logical steps, we are not missing anything. We are doing all logical steps, one to another, and we ended up being a formula which tells us how to move from one basis, from the standard basis to another basis. That's the formula that we obtained so far. So this is the place that I just summarized it. Okay, so this is what we found. B inverse Vs is equal to Vb, Vs, or equivalently. If you multiply B on this side, you will have exactly this one. If you multiply B inverse from this side, you will find this one. So from here to here, they are equivalent. This equation is equivalent to this equation. So what is the case like thinking about them like a map? So we have an R square and we have an R square. And we think of this R squared as a span of the standard basis. We think of this space as a span of B. When we are moving the vectors, so this is the vectors here expressed as coordinate vectors with respect to S. Here in this space, We are expressing our vectors as vectors, coordinate vectors with respect to the B. From this equation, as you see, from here to here, we are moving with B inverse, thinking as a map. So B inverse is a map. If I apply the B inverse as a map to this, I get VB. Right? You can use some other, there are many different notations applied as well. So you may see some notation, something like identity map, because it's an identity map. It is basically the vectors are exactly the same. It is identity map, but the representation of the vectors are different. It is identity. It is not exactly identity because the representatives are not identity, right? It is identity, but representatives are different. So be thinking of B inverse as a map. This is important for us because we will build it up more things on the top of it. Okay. Now we would like to consider another basis, C. This time we have B and we have C. We can do exactly the same things what we've done for B. Here we can set up the rules for C. It's another basis, it's another basis. It's the same thing. So shortly, we have, assume that we have C, you have these two vectors. They're not multiple each others. It means they are linearly independent. Then definitely C is a basis. So the matrix, set the matrix with the column vectors consist of the vectors of the spaces. So I have C1, C2. So this is the matrix C for me. Since C is a basis, these columns C1 and C2 are linearly independent. I have C inverse. This is what I said here. There exists a C inverse because the columns are linearly independent. Well, I have a still 2 by 2 matrix. It's easy to write it down. I will not make it longer. This time I'm just writing down the equation. 1 times 3 is 3 minus 4 is the determinant. Change these two positions. So this is 3, this is 1, and multiply these two positions by minus 1. But determinant is minus 1, so everything needs to be multiplied by minus 1 here. So you have minus 3, 2, 2, minus 1. So this is C inverse. With the construction, with the formula that we found, if we want to move from the vectors, with vectors, coordinate vectors with respect to the standard basis, to the coordinate vectors with respect to the base, another basis, we need to multiply C inverse. We need to multiply this matrix that we construct from the basis C. So this is what it is. So I'm thinking again the same vector, 1, 1. When I multiply by C inverse, I have minus 1, 1. So this will be the coordinate vector with respect to C, respect to another basis. Now, we also have 5 minus 4 is the coordinate vector with respect to B. That's what we calculate before. So the question is, in that moment, we would like to figure it out, how to move from this basis to this basis, or this basis to this basis. How can we move between these two bases? How can we move from the coordinate vectors with respect to the bases which are not standard bases? Okay, that's what we would like to do. We would like to find out a formula, a setting that will allow us to do that, moving from this coordinate vector with respect to C to the coordinate vector with respect to B, and vice versa. Okay, then we have R squared. We're looking at this vector spanned by the standard basis. And we have R squared. We are looking at this vector space as a span of B. So the basis of B in this case, basis of C in this case. And we have, again, thinking about the R squared. And this time we have for the basis of C here. So everything is moving with an identity map. We know how to move from here to here, here to here, here to here. We know how to move from these directions and these directions, but we don't know how to move from this direction, one way to another. So what we had from Vs to Vb, we were moving with B inverse. When we multiply B inverse Vs, we will get Vb. So if you multiply Vb by B, you get Vs. And so similarly, if you multiply Vs with C inverse, you will get Vc. You multiply this coordinate vector with C times this will give you the Vs. So this is what I am trying to say in all over those places, right? B inverse VC is VB. So this is what we figured out. Now our aim is to figure out how to move from here to here, the question mark. How to find out the identity map moving from this basis to this basis. How can we find the coordinate vectors moving from this basis to another, to this basis? That's the question. So this blue, this light blue things, it says exactly what we are going to do. This is this kind of diagrams are called is commutative diagrams. It is a subject of the category theory. It is a beautiful another theory of maths. So basically this one from here to here, and then if you move from here to here, it is equivalent to from here to here because, right, either you go longer or you go short. Exactly the same point. You start from here and from here, it should be the same. So if you start here, go up. Going up is C. But we need to think about that as a composite of the functions. That's what I wrote here, composite of functions. When you're moving with the as like a map. So first you apply C map, and then you apply B inverse map. So this is that one. B inverse C will give us that question mark place. So when we write it down, when we take the coordinate vector with respect to C and then apply B inverse C, tac, will give us the coordinate vector with respect to B. So this is what I wrote here. And this is exactly equivalent to this equation as well, because you're multiplying with from this side, multiply by B, and then multiply by C inverse, you will get VC, coordinate vectors with respect to C on this side, and then the coordinate vector with respect to B in this side, but you're applying the B map first and C inverse map. Okay, this means here, basically, you are going from this corner, right? You apply B first, and then C inverse first. Then you go from here to here. So this corresponds this expression. Here to here, B, and then C inverse. B, C inverse is this one. And we are moving from here to here. We want to move from here to here. Then we will go up and slide. Going up is C. This is why I have a C. Slide, I have B inverse from here to here. I hope this is clear. And let's see as the numbers. Now we understand as a formula, as a matrix multiplication, we set our formula. It is there. Now let's have a look as a number. So we have V here with respect to S. We have coordinate vectors with respect to B. This is coordinate vector with respect to C. Now I have a B matrix corresponding to B basis, and we calculate B inverse, C corresponding to basis C, and C inverse is the inverse of that matrix. According to what we just discussed, we need to calculate B inverse C matrix. multiply this matrix with respect to C, will give us 4 minus 3, 9 minus 7. As you know, you're multiplying row in the first column, first matrix, and together with the column in the second matrix with the dot product. So this times this, 6 minus 2 will be 4, and so on. 6 to 12 minus 3 is 9. Yeah. And then if we've just figured out that B inverse VC should give us the VB. Let's have a look. B inverse C VC, this is B inverse C, that what we calculated here, plugged it in. And the coordinate vectors with respect to C is minus 1, 1, plugged it in. If you multiply these two, 4 times minus 1 is minus 4 plus 9, it will be 5. Minus 3 minus 1 will be 3, minus 7 will be minus 4. Done. And this was exactly the coordinate with respect to P. So this is the justifications or clarification. It's an example of the theory that we set it out. Nothing is missing. It's just flow. It flows. The logic flows. I've just showed the other way around as well. If we take the coordinate vectors with respect to C, and then C inverse B, coordinate vector of the C can be obtained by C inverse B VB. So C inverse B it will be this matrix. If we multiply with this coordinate vector, then we will find out the coordinate vector of C. This is also the truth. So what we've done the base change from the standard basis to any basis for just the vector space. And then if we do, then we do any basis of the vector space to another basis of the vector space. How to move. That's what we've calculated so far. Now, everything in terms of the identity transformation, identity map. Now, if we change the identity map, maybe the linear transformation is not identity, is something else, then what will happen? How can we move the base change? So that's the next concept. Base change for a linear transformation. Why linear transformations are important in linear algebra is important for the vector spaces because they are not any maps. They are the maps preserving the linear structure, preserving the vector space structures. They preserve the vector addition, they preserve the scalar multiplication, so they preserve the vector space structure. That's not just a map. That's not just an assignment. It is an assignment preserving the structure. So this is why linear transformations are particularly important. If you have a linear transformations of vector spaces Rm to the Rn, we can always find a way to express that transformations with the matrix. And the linear transformation becomes a matrix multiplication, right? T times the vector will be coefficient with a matrix, which is a matrix form of this linear transformation, times the vector. So it's a matrix multiplication, or will give you the transformation. So A11x plus A12y is the definition of that. And this times this is the definition of the linear transformation. We can do both way. If you have a linear transformation, we can do that. So when we are doing it, basically it is standard basis for both sides. For the domain and a codomain, we are taking the standard basis. Now the question is, what will happen if, how can we figure out the matrix form for any basis for the domain and for codomain? And we are going to use the informations that we've just figured out. Now, assume that we have a linear transformation from domain And domain is we are thinking the domain of this transformation is a standard basis with respect to standard basis, and a codomain with respect to domain with respect to standard basis as codomain with respect to the standard basis. So the domain and codomain, both of them are standard basis. And the A, as I just showed, a matrix form for this linear transformation. Assume we have another basis for codomain, let's say B, and another basis for domain, let's say C. And then now our question is, what is the matrix form such that the basis of the codomain is B and the basis of the domain is C? How can we find out such a matrix form? The idea is the same. Moving up, cross down is exactly equivalent to moving from here to here. So the green arrow is equivalent to yellow part. It's a long, long way, and the short way are exactly the same. But we are thinking all of these steps as a composite of the maps. So we start from here. We want to go up. Now, this is a base change from B to S, so it will be B, right? So the first step is B, so that's B. Now, second step is just A. From here to here, we have the matrix A, so that's A. Now, from here to here, we are moving from the basis C, basis S, the standard basis, to the basis C. So from here to here, we move by C inverse, and that is a C inverse. So the matrix M has to be equal to C inverse AB. This is also equivalent to CMB inverse is equal to A. How I am moving from here to here, basically multiplying by I multiply here by C, multiplying here by B inverse. As you know, matrices are not commutative. You need to be very careful with the order. So you have to, right? You're multiplying from here by C. This will be identity. I will have CM here. Multiplying from this side by B inverse, then you will have an identity here, but I will have B inverse here. This is exactly what it is here. B inverse MC. This one and this one is equivalent, but just, yeah. I think it is clear for everyone. Let's do this with the numbers and let's see it is really there. It is happening. Right? We are not missing anything. Let's prove that. Before doing that, there exists a theoretical way to do this as well. So there exists a theorem how to move, tells you how to move, how to write a down matrix form of M directly, kind of a directly. How? Rather than doing the multiplication, but you will see whatever works. But usually we ask this form. If you have a linear transformation from V to W, and you're thinking the basis, codomain basis is V1, V2, Vn, and the domain basis is W1, 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 W2, Wm. That's that one. And here, the matrix form with respect to this basis, domain is the BW, codomain is BV, is expressed in this way. What is this? This one is a matrix such that each column of this matrix, you first take the basis elements here and apply the linear transformation and move to here. And when you arrive to here, which is TV1, that will be a basis, standard basis with respect to, this will be standard basis, coordinate vectors with respect to standard basis. Now you need to change that one into BW because you want to understand, you want the basis in this space be BW. So this is a base change here. Calculate TB1s, each of them, and then turn that coordinate system, coordinate vector with respect to the basis BW, for each of those vectors, put it in the columns, then you will have a matrix. That matrix is also a matrix representation with respect to the BV and BW, BV in the codomain and BW in domain. Okay, before I do calculation, I would like to express, because I'm going to take an example as a linear transformation from a polynomial space to to R. So I want to emphasize this fact. Everybody must know by now, but let me say it again to make it clear and to make everybody in the same page. What it is. So this is what we show in our classes, in our courses, uh, a space of polynomials of degree less than or equal to n. And this is the usual real vector spaces of dimension n plus 1. So in this vector space, n plus 1 dimensional vector space, because you have constant term plus a1t plus ant to the n, that is a polynomial of degree n, and all the coefficients, changing all the coefficients will give you dimensions. So a0, a1, an, so n plus 1 because of the constant term here. And this is a one-to-one correspondence between our n plus 1 as a vector space. There are many ways to take this correspondence, but I usually start from the constant term, I0, A1, or you can do it backwards as well. You can do AN minus 1 and A0. In whatever the question you're doing it, say to the person, this is what I'm doing, this is what is my assumption, because there are many ways to assume that, show that this is your assumption and apply the same assignment throughout your question, naturally. And this is S vector spaces because addition of the polynomials here is exactly the same thing, additions of the vectors here. And a scalar multiplication here is a scalar multiplication here. When you're thinking about the polynomials, you usually think about the ability to multiply the polynomials as well. But this has nothing to do with the vector space structure. So we are not talking about the multiplication. It is not known for us, for example, in that space. We don't care about that part of the polynomials. We assume that the polynomials as we can add them and we can multiply with the scalar multiplication. So it's a vector space structure. Then as vector space structure is isomorphic to the Rn plus 1. Okay. It is the same idea for the matrices. It is easier to use this part. It makes it a lot easier, a lot faster. And also you can use some computer aid as well, because it will be like a linear algebra. You will have the matrices, coefficient matrix, solutions of the linear system of equations. You will ask the computer, please calculate the reduced row echelon form for me. It will be done. It is an advantage to think with this way rather than this way. Even though you can set it up, your question, you understand your question and move to this way as a vector, then you can calculate a lot easier. And it's the same thing for the matrices as well. If you have a n by n matrices, they are isomorphic to 2 to the n because you have matrices. N by n matrix has 2 to the n components. I usually read by row, A11, A12, A1n, A21, A2n. So that is the correspondence that I choose, but there are many ways, of course. But if you do whatever your choice is, tell the reader that's what your choices are. Again, matrix, there exists a matrix multiplication. We don't care because we are looking at this isomorphism as a vector space. Isomorphism is a vector space case. And matrix addition is a vector addition here. Matrix scalar multiplication with the matrices, you're multiplying every element. Your scalar multiplication here, you're multiplying scalar with every component of the vector. So it's perfectly fine. As a vector spaces, they are the same. No problem. Okay, what is the question that I would like to do is we have P1. It's the one degree polynomials, linear polynomials. and going to the R2 space and given by this rule. The rule says if you have a polynomial a plus bt, the first component will be a minus b and second component plus a plus b. So this is a linear transformation. It is assume that it is given. You can prove it if you like. And we know that standard basis for P1 is 1 and t, right? Everything is a linear combination of 1 and t. So it's spanned by it, and 1 and t are linearly independent because they are not multiple of each other. They are standard basis. So if you want to write it down, basis, the matrix form for this linear transformation, such that the standard basis with respect to standard basis for domain and codomain, we will just calculate the T1 and TT. So T1 is, as a polynomial, will be 1 plus 0t. That will be 1, a minus b, 1 minus 0. A plus b will be 1 plus 0. So this is 1, 1. TT will be t 0 plus 1t. So a is 0, b is 1. A minus b, so that's 0 minus 1. A plus b, 0 plus 1. So it is just minus 1, 1. So T1 with respect to standard basis, in this case, 1 minus 1, 1, 1 is the matrix form of this linear transformation. I just would like to remind you, just in a little corner, A plus BT is really isomorphic to AB, and 1 in this case will be corresponding E1, and T will be corresponding E2. I just would like to remind you of this situation. Okay, now I just carried forward the informations that we've just done. This was another basis of R2, and these are the columns B, B inverse, and this was another basis of R2, and that's C, C inverse. Now we would like to find out that M that we were talking about. That is this matrix form with respect to the basis in codomain B and domain is C. And we calculated that the M matrix is a C inverse AB. So, and this is A matrix that we've calculated. So that's C inverse, that's B. If we multiply them, we will find this matrix. So this times this will give you this matrix. And this times this will give you this matrix. So this matrix is the matrix form of T with respect to the domain C and codomain B. And also, the theory tells us that calculate the TB1 and to change the coordinates vector with respect to C, find calculate TB2 and change the coordinate system with C. This should be equal to exactly this matrix that we found. So I'm trying to find out same result in two ways, and two ways that I gave. Okay. Let's do that. Let's see this part is exactly this matrix and how it works. So TB1, B1 is 1, 5, and this was the rule of the linear transformation. We were A minus B, A plus B. So A minus B, 1 minus 5, so that 1 is 4. A plus B, 1 plus 5 is 6. So TB2 will be 1, 6. That will be 1 minus 6 minus 5. This plus this will be the 7. So this is the coordinate vector with respect to the standard basis now. We haven't used any information about the standard basis C. Now this is what we need to do. Change this vector, this coordinate vector standard basis with S, to coordinate vector with respect to standard basis C. This is what I've said here. Now we need to move from the basis C, basis S, standard basis, to the basis C. This is what we need to do. From here to here, while we are passing, we are looking at as a map. And in that case, we are just multiplying by C inverse. So we need to multiply C inverse of these vectors. If you C inverse times this was the C inverse. C inverse times this vector gives us the 24 minus 14. And C inverse times this vector gives us a 2917. And this is exactly the matrix that we were talking about. That's exactly. So we found this way and we found this way. So, right. We found the way, like thinking of this shape. And we also found with the theoretical way this way. Right. Both of them is done. So this is the base change with respect to base change of the vector spaces and the base change with respect to linear transformations. What's the matrix form with respect to different bases, and also vector space. How you look at the vector space with the different bases, and how you move on from standard to anywhere, so any, or if you have any two, and how to move it on. That's an important subject, and important in many other layers of the maths as well. I hope you enjoyed it. Thank you very much. All the best.